Okay, so you guys should know this about the Bohr model. You should be able to answer a couple of questions. Bohr broke the atom into two significant parts. If I ask you what the significant parts of an atom are, location-wise, not particle-wise, Tayden, can you tell me those significant parts?
You mean like not positive, negative?
Nope, I don't want to know the particles. Think about where those things would be found. Okay, so one of them is the nucleus of the atom. And what name or what do we talk about in that space that's outside of the nucleus?
Energy levels.
Good. So he broke it into those two things. Energy levels and nucleus. So let's just like, since it's been a while, let's review it a little bit. If I were to ask you, or if I were to say to you, one of these is dense and small, one of them's a lot of empty space. Could you tell me which was which? Yeah? Jacqueline, what would you tell me?
The nucleus is the dense.
Okay. So this is a dense. I'm going to say in compact. So if she tells me the nucleus is dense and compact, would y'all agree that the energy levels, there's a lot of empty space? Okay, so this I will say is mostly empty space. Now what if I ask you a question about the nucleus and its charge? Is it neutral? Does it have a charge if I speak just of the nucleus in general? What do you think, Caitlin? Neutral or have a charge? Okay, she says neutral. No, what do you think?
I think it has a positive charge.
He thinks it has a positive charge. Why do you think that?
Because neutrons don't have charge.
Neutrons have no charge. What else is in the nucleus? Oh, we probably should write that down. I find protons and neutrons here. No charge and a positive charge, so yes, this is a positively charged area. All right, so then what would you tell me about the area outside of the nucleus where I would find energy levels? Jacqueline?
It's where the electrons are and has a negative.
Okay, so we've got electrons here, and it is a negatively charged area. That's all old news. We should all know that. Right? So up until now, I guess, my question would be, how have we thought? Or like when you were in junior high, or maybe you were over there in Mrs. Weldy's physical science class, how did you think about the energy levels and the electrons? Like, what's the picture in your brain like when you think about that? Do you have one? Could you draw one? Oh, try to draw one. When you're done, stand up. I only want to know about the energy levels, really, in the end. So just out of curiosity, check with someone around you. I just want to know if they all look the same. Do they all look the same? Yeah? Yeah? Where are your electrons? In the energy, what's your energy level look like? It's a circle! With some little e's in it, maybe? I don't know how you wrote them. Yeah. So that's how we've been thinking about them all along. Guess what?
It's wrong.
That is not correct.
Is it a triangle?
So, it is not a triangle. It's not that simple. So we need to talk about that. We need to talk about the electrons in energy levels. First of all, Bohr says that electrons are found only in specific paths. He said they were circular. We'll talk more about that later. I'm going to put a sad face here because he was wrong. Wrong, wrong, wrong. He was right about one energy level, but all of the rest of them he was wrong about. He did say they orbit the nucleus. That was correct. He got that one right. So this is an X, this is a check, really, if you think about it that way. He also said electrons follow a set path. That was correct. It wasn't the circular path that he thought once you get past the first energy level, but it was a set path. Okay, so now I want to talk a little bit, like very specifically about the energy levels. We'll continue with that. And I want you to pull up that handout that I had you get when you came in. I need to find one. All right. So I want you to look at that handout, and we're going to talk about it a little bit. I'm going to have you write some things down. I want you to find this page that has the ladder on it, because it's a pretty good example of what we're going to talk about. I want you to label this green area beneath the ladder. I don't know if that's shown up very well. Nucleus. So go ahead and write that on your paper. So that grass that the ladder is sitting on is like the nucleus. And then I have this ladder, and I want you to think of each rung on the ladder as an energy level. So I want you to go in there, and I want you to write 1, 2, 3, 4, 5, 6, 7, 8, 9. So you just want to number them so you'll have like a reference to know what I'm talking about. That might make you be able to see it a little bit better. I also want you to put on this paper N equals the symbol for an energy level. So if you see something like, give you an example, N equals 3, you would come down here and you would look at the third energy level. If you had a diagram, you'd look at the third energy level. If you were trying to figure something out and you have N equals 3, you're specifically talking about the third energy level. Now I'm going to move this and we're going to write some stuff down, but keep it out because you're going to have to look at it. So if I look at the energy levels, I can say they're like the rungs on the ladder. And then I'm going to ask you, that was bad, some questions about them. my first question, I want you to look at the diagram, and I want you to tell me, based on that diagram, are these rungs equally or unequally spaced? What would you say, Marty? Equally or unequally? Okay, so the rungs, or energy levels, we're going to use EL from now on for that. The rungs, or the energy levels, are unequally spaced. That's exactly how it is in an atom. Okay, so now I'm going to ask you another question. I want you to look at your picture and see if you can figure it out. Which energy levels are the closest together? Those farthest from the nucleus or those closest to the nucleus? Which ones are the closest together? The ones that are farther from the nucleus or the ones that are closer to the nucleus? Connor? Okay, so the farther from the nucleus you are, the closer the energy levels are to each other. So the farther out I move from the nucleus, the closer the energy levels are. Now, we're going to get to this eventually, but I want you to think about that for a minute. The farther away from the nucleus, the closer together my energy levels get. Why do you think that might happen? Do you have any idea yet why that might happen? Think about the question. The farther away from the nucleus, the closer the energy levels are to each other. No idea yet? Okay, I just wanted to know. We'll get there. So I'll ask you another question. This one you should be able to figure out. If you were actually climbing that ladder, would it take you more energy to get from the nucleus to the first energy level, or to get from the 8th to the 9th energy level? Which would require more energy of you? To get from the nucleus, the empty space, to the first energy level, or from the 8th to the 9th energy level? What do you think? Jacob, what do you think?
The 8th to the 9th.
Okay, anybody agree with him or disagree with him? What would you say, Jacqueline?
Nucleus is first.
Okay, Tayden, if you agree with Jacqueline. Okay, so Tayden, why would you say that?
Because it's a farther distance.
It's a bigger step, right? You gotta lift yourself farther. So, it does take more energy to move between the lower energy levels than it does the higher energy levels. So let's put that in words. We'll say it takes less energy for an electron to move between higher energy levels than it does lower energy levels. Does that make sense to everybody? So he figured all of those things out. What he didn't figure out, really, were some other things that we need to know before we can work with the atom. So also going on at the same time, scientists are starting to notice or think about some things. Now, certainly, this isn't the first time they notice them, but they start to wonder why they're happening. And let's see if you can relate to these things. I'm going to let you write it down, then I'm going to ask you some things to think about. How many of you have been to a bonfire before? Is that everyone? Anybody not been to a bonfire? Okay, how many of you have roasted marshmallows or hot dogs or whatever and used those fancy sticks, not just like you broke them off the tree kind of stick, right? What's at the end of those fancy sticks?
Like the two little prongs.
Oh, the two little prongs, where we put the marshmallow or the hot dog. Now, what happens when I put that in the fire to the prongs and the metal? If I leave it in there long enough, what happens? It'll turn red. If I leave it in there a little longer, what color does it turn? Do you know? Have you watched this? Yes, it goes from red to yellow to white. Same process they use when they brand, that light drives me crazy. Same process they use when they brand cattle, right? They heat that iron up until it's red hot, a little past red hot, so they can brand cattle. It's the same process that a farrier uses when he puts shoes on a horse. Have you seen that before? They heat the horseshoe up so it's red hot, yellow hot, so they can bend it to fit the horse's hoof the way that it should. So they start to notice, or they start to think like, ooh, why does that metal glow when I heat it up? They also start to notice things like, and you should notice this too, when I'm walking outside on a very sunny day, through a parking lot, let's say, and the light is hitting a metal object just right, you notice how it like hurts your eyes, or you see it very brilliantly? They were trying to figure out why that happened. Then the other thing they noticed is, if they ran electricity through certain gases, it was no longer clear, it became a color. Why does that happen? How many of you live on a farm? You don't even have to live on a farm for this. How many of you have an outside light, like a barn light that comes on at night? Anybody? Have you ever looked at what color it is? Anybody have one that's kind of yellow? I do. That's called a sodium vapor lamp. Why is it yellow? Because when I run electricity through sodium, it glows yellow. It's super cool. You drive around and you don't even think about that, right? Caitlin, wake up. It's not that boring. I can make different chemicals for you. Actually, you're going to make chemicals. We're going to run electricity through them. We're going to run energy through them using the Bunsen burners. And you'll see the colors that they glow. So they start asking all these questions like, what's making these things happen? So maybe we just write down in your notes, glowing objects, which would be, what should I say? I'm just going to write fork. You guys will know what I'm talking about. Fork, metal, and gas. We're not going to write down all those things. I just want you to think about that. Can't figure any of that out. Along comes this guy after Bohr, named Schrödinger. And he's super important. And he helps us answer all these questions, him and Albert Einstein. He comes up with something called the quantum mechanical model. We're going to call it QMM from here on out. We're not going to keep writing that. Basically, this is the modern description of the atom. Okay, so let's say, carry this over. Quantum mechanical model does a lot of things. It determines the possible energies of an electron. It determines how likely an electron is to be in a specific location around the nucleus. This right here, we're going to talk about this and look at some pictures. This is called probability. Like in math, sort of. Now, basically, this is going to help us figure out how likely we are to find an electron in a certain location. We can't think about them just traveling around that ring anymore. If I bring this fan up here and I say, okay, here's my fan, and I will say too, the fan blades are the electrons. See that? When the electrons are not moving, it's really easy to tell me how many there are, is it not? How many electrons does my atom have? I can think about this as the nucleus, and these are my electrons outside in my first energy level. Now watch what happens. Do electrons sit still, Kyle? No, they do not. So I don't want my fan blades to sit still. Let's turn them on. Now, how easy is it to see the electrons? Isn't that fun? Can you see them, Riley? If I started like this, could you tell me how many there were? No, that's what the electron cloud is like. All of the electrons are in different locations, spinning around and moving. So if you, let's see, if I turn it down, oh, that's the lowest. That's a good fan. If I turn it off, obviously they slow down. It becomes easier to see them. Now, if you look at this little handout that we have, if we want to see that diagram-wise, I put a couple pictures in here. Let's look at, well, let's look at this one first. So this is our old idea. Maybe draw an arrow. That's actually the Bohr model. This is the new or modern model. We know the nucleus is there, and we know outside the nucleus are the electrons. If I flip to the other picture, that's an even better picture, shows me the nucleus, and it shows me the electron cloud. The darker the area, and you probably should write this on your paper, the darker the area, when you see one of these diagrams, because you will, the darker the area, the more likely to find an electron, and I should probably move this so you can see. The darker the area in the diagram, the more likely you are to find an electron in that area. So that should tell us, if I look at this, and I know that somewhere out in all of this are my energy levels, based on what you see in this diagram, is the darker area closer or farther away from the nucleus? Closer or farther away? The dark area. Look at it, figure it out. What do you think? Connor? Closer. So do I have more likelihood of finding an electron in the first energy level, or let's say the 7th out there? The first. So by first energy levels, this tells us first energy level fills with electrons first. That makes perfect sense. And maybe, I don't know, just so you'll remember it, let's write fan blade on there. That'll help you remember what I showed you. All right, just a little bit more. All right, so when we see all this light, like the light that you're seeing right now, it happens because we're moving electrons. All light. If I want to move electrons, there's this word that I use, or that goes along with it, and it's called a quantum. One quantum equals the energy needed to move one electron from one energy level to the next energy level. So if I add one quantum of energy, I can make that electron jump to the next energy level. Quantum is singular. It's when I'm working with one electron. Quanta is plural, and I use it when I'm talking about multiple electrons. Like I would say, if I have one electron moving from the second to the third energy level, I would say it takes one quantum. If I have three moving, I would say that it takes 3 quanta of energy. So singular versus plural. And remember, the higher the energy level, the lower the energy needed to move the electron. All right, so now, this is the part that lets us get even closer to lab and some problem solving. We describe electrons using quantum numbers. And there are 4 of them. We only really worry about 2 of them in Chem 1. So I'm going to get through these today. The first one is called principal quantum number, and it's an easy one to remember. Okay, so principal quantum number tells me the number of the energy level the electron is located in. Now see if you can remember this. What's the symbol for energy level? Do you remember? If you don't, flip back and look. We wrote it down already. It's a letter. It's a letter. Yes. N. It is N. So this is represented by N. And we will say that N for you guys is going to equal 1 to 7. So we're going to only work up to 7 energy levels. It really could go to infinity. We don't really know. We don't know if we've discovered everything we need to discover or we can discover yet. So that's the first one that we're going to be concerned with, principal quantum number, and that's just the energy level. And the second one is called the orbital quantum number. And when we talk about the orbital quantum number, we're really talking about, it's called an atomic orbital, and that's where we're likely to find the electron. For each energy level greater than 1, there's more than one possible location for electrons. Multiple locations. What time do we get out of here? Okay, I'm going to have you write something down real quick and then I'll stop. Let's just add that each orbital has a different